Hello, everyone. I am glad to participate in this important forum to discuss this kind of strategies towards a circular economy for the built environment. Today, I want to share with you some of the work that I have done in the field of disassembly strategies for adaptive reuse of buildings. This is a brief outline with the points in this presentation. I will start with the background and motivation of my research work. Then I will follow up with a research overview and the presentation of some methods and tools that I have developed in the field of disassembly planning. I will finish with a summary of the work done, as well as the limitations and future work. Let's start. In an era of climate change mitigation and adaptation, efficient use of the natural resources is considered as a practical means to increase sustainability in urban settlements. From a life cycle perspective, buildings contribute significantly to the global environmental load caused by human activities. For example, the building industry is responsible for 30% of the world's resource depletion. At the same time, it is responsible for the 40% of the waste production to landfills. These numbers reveal a huge inefficiency in the use of the natural resources that are more and more scarce day by day. Now, a shift of thinking in the perception of sustainability in the construction industry has arisen in the last decade, switching from the traditional creative and innovative approach towards a restorative and regenerative one. This change of perception is founded in the fact that an enormous proportion of extracted materials along human history are in today's built environment, and is gonna keep increasing in the coming decades. The turnover rate of the building stock is low. Therefore, we cannot just rely in the new construction of energy efficient assets. The relative importance of the extraction and construction life cycle stages have increased because of the reduction of the energy loads in the operational phase. And finally, the price of materials extraction is increasing, as is the negative environmental impacts due to natural constraints. To remedy this situation, the construction industry is implementing designs and systems with improved life cycle performance. The main objective is to consider closed loop cycles. The principle of closed loop cycles aims to keep products, components, and materials at their highest utility and value as much as possible in order to create sustainable cycles. One example of these trends is product recovery management, PRM. In this matter, adaptive reuse of buildings has been identified as a superior alternative in terms of sustainability and circular economy. It involves restoring and in some cases changing the use of existing buildings that are obsolete. Adaptive reuse is considered as a disruptive practice in the current capital project delivery model for the renewal of today's built environment. In a life cycle perspective, adaptive reuse has the potential to maximize the residual utility and value of existing assets by giving them new life through PRM methods, such as selective disassembly and deconstruction planning. Unfortunately, the current implementation of adaptive reuse relies on conventional intuitive planning procedures by professionals, leading to suboptimal results. This problem is due to the lack of development of PRM methods to assist during the process of adaptive reuse planning. The aim of my research interest is to develop a technical framework for improving the net environmental impacts of new buildings through product recovery management methods and tools. In an overview, my research is divided in two main branches. The first one is focused in the analysis of macro structures, such as supply chains for reused components and the role of adaptive reuse inside the circular economy. The second one is focused in the development of optimization methods for adaptive reuse of simple structures. In this presentation, I want to focus in the second branch related to disassembly strategies for adaptive reuse of buildings. The main contributions for this part is the optimization methods that are related to the process of selective disassembly planning of buildings. Now, in the process of adaptive reuse, it is necessary to take out parts from the old design to refurbish or replace. However, if a threshold is exceeded, adaptive reuse could not produce environmental savings anymore, and it could become more costly than new construction. Therefore, the selective disassembly planning has to be performed efficiently. In first instance, we developed a disassembly planning approach for buildings. The field of disassembly planning and deconstruction for buildings have been studied for the last 20 years. However, the research has been focused on the complete disassembly with fixed activity networks. In contrast, the field of selective disassembly has remained unexplored and underdeveloped. In 2018, we developed the first in its class selective disassembly planning for buildings method, or SDPB. The SDPB method is based on heuristic optimization and the disassembly structure graphs theory. The method optimizes disassembly plans for retrieving selective components, for example, the steel beam C7. The method seeks to minimize the number of disassembled components by using a rule-based recursive analysis based upon physical, environmental, and economic constraints. This method is able to find efficient, practical, and realistic solutions. This has been validated through functional demonstrations with case studies. Some of the conclusions in this part of the study are: buildings disassembly planning can improve the environmental and economic performance of adaptive reuse projects through appropriate product recovery management. Also, this method represents an advance for improving the technical inefficiencies in renovation projects, making them more affordable. Finally, the level of detail of the disassembly model has been identified as a critical factor in order to ensure the feasibility of the proposed methodology. A very detailed modeling could increase unnecessarily the complexity of the optimization analysis. As an extension of the previous work, we developed a selective deconstruction programming tool. Today's built environment is integrated by recurrent, repetitive building subsystems and modules. In this matter, existing assets with recurrent building subsystems represent a good opportunity to take advantage of the intensive and detailed design process for adaptive reuse, including the selective disassembly planning. Therefore, we developed a tool for selective deconstruction planning and scheduling, and we validated through a functional demonstration in a case study. In 2017, an entire corridor of rooms located on the second floor of the E2 building was redeveloped as part of an adaptive reuse project in the University of Waterloo. Our method is able to analyze specific subsets of the 6D model. The method estimates the deconstruction programming of the works in an automated way by extracting the metadata generated from the SDPB approach. This approach optimizes the disassembly plans for multiple targets and then merges them all into a single deconstruction program. For example, for retrieving the component C7 in the figure, the critical path of the deconstruction program is calculated with the duration, cost, and environmental impacts. In conclusion, this study develops and validates a pioneer selective deconstruction programming approach. Also, corrected deconstruction programming has the potential of improving adaptive reuse performance. And finally, this approach improves the project's performance through process automation. In the last stage of our investigations, we developed a multi-objective optimization analysis for selective disassembly. First, the SDPV method is used to generate the disassembly plan for retrieving single or multiple components. Once the disassembly plan is ready, more deconstruction methods per component are included. Then, a weighted multi-objective optimization is implemented in order to generate the set of non-inferior solutions that minimizes environmental impacts and building cost. After finding the set of non-inferior solutions, the decision makers have the responsibility of choosing the best alternative for the project. As it is shown in the figure, this becomes an iterative process whereby if the project needs are not fulfilled, the adaptive reuse design should be changed by the designers. We developed the 60 beam archetypal as well as the disassembly model of the subassembly displayed in this figure. First, the SDPV method creates the disassembly plan for target components. For example, for retrieving the components C7 and C13. In the next step, the multi-objective optimization is performed. The results show that different complete disassembly plans exist for all the possible combinations. The possible combinations are driven by the deconstruction methods per component, as well as the dismantling interdependence. The solution A represents the most eco-friendly alternative because it is the one that reduces the negative environmental loads. In contrast, the solution K represents the most cost-effective option. Now, even though the potential benefits for implementing adaptive reuse, there are several barriers in different domains that limits its current application. The field of barriers to adaptive reuse has been studied and documented in depth due to the importance of the topic. The framework and the methods developed in my research aims to tackle some of the technical barriers, such as physical restrictions, technical difficulties, and inaccuracy of information, and even drawings. Also, there are other kind of barriers related to the resource-based business model, such as the inertia of production, commercial risk, and financial perceptions. In this matter, the use of BIM for adaptive reuse has the potential for optimizing the project outcomes. However, current BIM models do not support important project activities for adaptive reuse, such as disassembly planning, product recovery management, or parametric design to integrate recovered products in a new design. Therefore, in another study, we developed and integrated a BIM process model for adaptive reuse project execution planning. In this approach, we take advantage of the intelligent 3D model-based processes of BIM for adaptive reuse projects. And in a first example, we developed an automated script to add meaningful information to the BIM elements during the modeling process. This information is fundamental to compute the disassembly planning of target components, such as type of part, disassembly part ID, and hosted components. For a second example, we developed an automated script in order to extract relevant information from the BIM model for the deconstruction planning. This information is fundamental and necessary for determining the deconstruction sequences of target components to retrieve, such as motion constraints for components and extraction directions for connections. With the information generated and retrieved from the BIM model, now it is possible to apply methodologies for selective disassembly and deconstruction planning. One of the main limitations of the methodologies and tools presented is that their accuracy depends on the accuracy of the input data. In this matter, the available data for deconstruction works is very limited to only a few options according to the most common trends in the construction industry. Therefore, we had to make some assumptions for the estimation of some missing data. Some of the following research stages will be the analysis across the building stock in order to determine the global potential benefits of adaptive reuse or reuse of building components. Also, there is a need for the incorporation of complex deconstruction methods. In addition, there are parallel areas of opportunity to keep developing the methods for improving the dismantling of buildings. For example, selective modular disassembly planning and testing alternative optimization methods. Also, some of the alternative applications of the methods presented are designing for future adaptability of buildings. With these methods, it will be possible to create green building designs that are very efficient for the future disassembly or adaptation. Also, it will be possible to develop training tools for deconstruction works by using virtual reality. In addition, there are new business models arising in the field of circular economy for real estate market, where buildings are designed as the future raw material banks. In addition, we are living in an era of technological advancements that are making possible the improvement of buildings' performance along all the life cycle and along the entire construction supply chain. For example, it has been demonstrated that digitizing building information is reshaping the ways for delivering buildings. Digitizing the built environment is leading to a greater integration across practices and skills that were once considered separately. This integration is helping to create technical solutions and new functional business models in the field of circular economy, with the purpose to move towards a more sustainable environment. And all this research has been developed in collaboration with colleagues from my alma mater, the University of Waterloo in Canada, also the Technological University of Berlin in Germany, and Chalmers University in Sweden. We are pleased that the acceptation of our ideas have been well received, and we believe in the future potential that they have. And finalizing, I am very committed with the vision and motivation of the presented work, and I will work continuously towards the development of this kind of innovative approaches for sustainability in construction. And thanks a lot for listening.